are good to go. Okay, so heat of formation. So this PowerPoint's really short as well. The key thing that I want us to learn is this last slide here. This will be the key point that we actually talk about. But with the heat of formation, um, the way that it's written is delta H degree F. And if I were to actually write this out in pencil, it would look like delta H degree, and then the F would be down as a subscript like such. That is the amount of heat given off when 1 mole of a compound is formed from its component elements. And the key idea here is that it must be 1 mole of something. So below, we have a reaction here that's H2, 1/2 oxygen, H2O. So normally, we've written this reaction out a number of times before, and when we've done so, we've called it 2H2 plus O2, and then we've said that goes to form 2H2O. What they've done here is they've said this 2H2O, this is no good because I want to know the heat of formation for only 1 mole. Right now, I'm forming 2 moles of this, and that is unacceptable. And so what they do is they divide each of the coefficients. They divide each of the coefficients, which are these little front numbers. Again, this would be a 1 by 2. And so you end up 2 divided by 2 is 1, so H2. 1 divided by 2 is a half, and then 2 divided by 2 is 1 again. And so that's where that equation got derived from. These values here, so this 285.8, if you use the physical science data table, it's super blurry on my OneNote, but you have all of the data and all of the delta HFs for all of these different compounds. So again, H2O liquid, negative 285.8. Well, negative 285.8 would mean that it was an exothermic reaction, or that would be the heat of formation. So you could write it again this bottom way or this way in the reaction up here. Okay. Moving forward, key thing, again, this is repeated twice in here because it must be important. Remember that this value is only for the formation of 1 mole from its elements. This is only a special heat of reaction when 1 mole of substance is formed. Note the heat of formation of pure substances like H2, Cl2, Al, etc. is just 0 kilojoules per mole. So this would be if it was like just the element. So in other words, not a compound. So not a molecular or not an ionic compound. If it was just a pure element, the heat of formation is 0 kilojoules. When writing the heat of formation reactions, remember the following. The equation must be balanced so that 1 mole of the product is produced. The diatomic elements are Hofbrinkel, or you can use the 7 of 7 rule to remember that. So it starts at element number 7, which is nitrogen, and then you draw a 7 going from there. And then don't forget to include hydrogen. And then the reactants must be elements, not polyatomic ions. The reactants must be elements, not polyatomic ions. All right. So looking at these two particular reactions, we want to write the heat of formation reactions for the following compounds. So we want to be able to form this MgO, and we want to do so using elements. And so what I would do first is I would go to my little table here, and I would look up MgO. Here I can see that MgO is negative 601.7. That's the value. So I would probably write that down first. I'd say delta H is equal to negative 601.7. I think it's kilojoules. Let's just confirm that. Negative 601.7, and the unit is kilojoules per mole. Wonderful. And so what I would do is I'd try to say, well, the only way I can make magnesium oxide there is if I combine magnesium and oxygen. And when I do this, I would have to remember, okay, oxygen's diatomic. Well, great. Now I'd need to balance this reaction. I have 2 oxygens, so I'd need a 2 here and a 2 there. But what I've done now is I've actually got 2 moles of this product, and that's not good. I want to have only 1 mole of it. So we need to divide each of these by 2. When you do so, you get Mg plus 1/2 O2 goes to form MgO. And because this delta H is negative, I would write it here and say plus 601.7 kilojoules. And that would be the heat of formation reaction for magnesium oxide. The CaCO3 reaction, that one can be a little bit more confusing in terms of finding its actual heat of formation. Um, every time that I Googled it, the only reaction that I actually got for this one broke the last rule. So it broke that the reactants must be elements, not polyatomic ions. Um, so when I did that and when I looked it up, this rule actually got broken. And so here was what I found online. I found that CaO plus CO2 goes to form CaCO3. So these are not, they're polyatomic, but they're not ions. Neither of these two have a charge on them. And the way that this would work is Ca2 plus and O2 minus. That would be how those two would come together. In the second one, carbon has a +4 charge, and then you have two oxygens with -2 charges. And so those would all balance out in the sense of you have +4, -2, -2. That has a neutral or 0 charge. Calcium oxide has a +2 and a -2 charge. So that one breaks rule number 3 in terms of its heat of formation. And then what we would do is we would look up CaO, CaCO3 on our little table that is in your data reference booklet. This is on the page after specific heats. And when you find CaCO3, you would see that the value is negative 1,206.9. And so I would add that on the product side as 1,206.9 kilojoules, like such. And that would be how you would write the heat of formation reactions for the following compounds. Let's put a line right through here. Those are the two. Does anyone have any questions about those steps there? Okay. Awesome. So if we look back at our equation for water, how much energy is released if 2 moles are created? So again, we said that we balance this reaction in this weird way with the 1/2 prefix, balancing coefficient there, so that we could, wow, I cannot draw a straight line on this drawing tablet, so that we could have 1 mole of H2O being produced for every time this reaction happens, and that gave us this value here. If 2 moles of water are produced, we would need to multiply this number by 2. And so we can find the enthalpy of any number of moles of the product formed by multiplying the enthalpy by the number of moles. So in other words, if 2 moles of water were formed, we would get negative 571.6 kilojoules if 2 moles of water were formed. Okay. That gives us a lot of power because what that allows us to do is that allows us to have a number of grams of something and convert that number of grams into a number of kilojoules of heat and be able to see exactly how we could get there. So I'm going to just write this equation out again. H2 plus 1/2 O2 goes to form H2O, and the value we had was negative 285 plus 285.8 kilojoules. So if I know how many grams of water I have, I can also figure out how many moles of water I have. And if I can get to moles of water, then I can also get to kilojoules based on what we just learned here. So what I'm going to do here first is I'm going to start with the only thing I have a number and a unit for, 25.0 grams of H2O. Times sign line. I need to convert to moles of H2O. And I know that the mass of oxygen would be 1.07 times 2 plus 16, which would be 18. And I remember it as 18.0148. That's just how I have it stored in my memory. Now, the units of this delta H are really important. The units are kilojoules per mole of water. Right now, all we've done is we've gotten out of grams of water, we've canceled out this, and now we're in moles of water. And so as such, what I can do is I can plug this in as 258 285.8 kilojoules per 1 mole of water. This is a known conversion value. In other words, that fraction, if we were to divide 285.8 kilojoules per 1 mole of water, that fraction just cancels out and is equal to 1. Similar to what we do here, where yes, we are dividing by 18.0148 and multiplying by 1, but we said that entire fraction, that 1 mole of water, was equal to 18.0148 grams of water. In the same way, 285.8 kilojoules is equal to 1 mole of water. And then when we plug this into our calculator, we would go 25 divided by 18.0148 times 285.8, and we would get a final value here, final delta H degree value, equal to negative 396.618 kilojoules. And that would be the final answer to that question there. Does anyone have any questions about these couple problems that we did today?